Before like we even begin, I'm gonna have to be honest with you.
Sure.
Yes, this video is specifically for my not specific. It is for my best friend to watch
Yes.
specifically, but then I'm also going to be putting it on my YouTube. It just has like 20 subscribers. Yeah, but just in case, yes, it's small, but I don't know if they are interested in watching physics.
Yeah.
No, people don't
Actually,
want
these days a lot of people are
yes.
physics is dying, yeah. But
Yeah.
don't
But
need
you
to
never
discourage
know,
people.
maybe one time, maybe, because when a video goes on the internet, for as long as that platform exists, it's gonna be there forever. But you never know, maybe one day some kid out there is interested in physics and they find it.
Let's do this for that one.
Let's do it for that one kid. I used to have problems like when I just began in my first year as a civil engineer. I'm sorry, as a civil engineering student, I used to try and look on YouTube for inspiration for people doing civil engineering to inspire me. And those few people that I found, I think was really good for me. And so I think this would also could also be nice for whichever kid in the future. Yeah. And I think it's also going to be a learning experience for me. Me, I like to learn, and I like to listen to people like talk about things they're interested in. So someone can be talking about flowers, and I'm gonna be listening, or bricks or stars, and me, I will be ready to listen. As long as someone is you're interested in physics, right?
Yes, of course.
All right. So
yeah, that's actually a nice way to live.
yeah.
Every person has something to offer, right? Something they are interested in.
Yeah.
And yeah, people can have different views on life. And it would be interesting, yeah, as you said.
Yeah.
Even they could be interested in flowers. Okay, that tells you something about them.
Yeah.
So I think it's interesting to
I'm gonna
listen to people.
close this window because of that noise outside. Let me just close a little so some air can still pass through. Yeah, so what is your name? Tell the people your name, where are you from? Yeah.
So I am Filman Andong.
Yes.
I'm from Eritrea. I was born there, lived there for the rest of my life.
Yeah.
And I came to China in 2019 to do my master's. So I did my bachelor back home.
Yes.
I finished my undergraduate in 2016.
Okay.
Then I worked for like 3.5-4 years as a assistant lecturer in the school I was teaching in.
Oh, okay.
So, yeah, I was responsible for those freshman students doing freshman physics.
Yeah.
And second year students who have already started their majors, physics major. We were teaching them laboratory physics, like experimental physics.
Yeah.
So we were doing those things. And in 2019, I came here to pursue my master's.
Yeah. So you got your bachelor's in physics also?
Yeah, applied physics.
Yeah.
Applied physics.
I remember like having a conversation with you on this. I feel like you said something in the lines of at the beginning you didn't start with physics.
Actually, when in 2010, when we finished in our high school, you have this matriculation exam, and then like based on those results, you get to choose what you want to pursue. Yeah. And there's always that stigma where people who scored higher, they always go into medicine or engineering.
Yes. Everywhere.
Everywhere is the same, I guess.
Yeah.
And at that point, I was a victim of that because deep down, I knew I wanted to do physics. Yeah. But there's always people telling you, what's the point? Like, you're just going to be a teacher. What's the point in pursuing physics?
I wanted to ask you that at some point during this.
We'll come to it.
We'll get to that.
But yeah, those were the things among my friends. Before I made that decision, they were giving me this talks.
Yes.
Right? you're just going to be a teacher at some point. So there's no future into it.
Yeah.
So why not go to those professions where you can like make money and make a living and stuff?
Yeah.
And actually, I did. The first time I chose the major, I went for engineering.
Yes.
But we have to do like, even when you go to college, you have to do 1 year of like preparatory courses.
Oh.
So you're not an electrical engineer, you're just doing engineering. You take some engineering courses.
Yeah.
So on the second year, you get to choose electrical or civil and these things.
Yes.
So I chose that engineering. I came to that school and to the college. So I started doing it for 1 month. That's when it got to me like, okay, I'm going to do this for 1 year. So what am I going to study then? Is it going to be electrical, is it civil or mechanical and these things?
Yeah.
I don't mean any offense by that, but to me, none of them like stood out
Yes.
to be okay. This is the one I wanted to do.
Yeah.
But still, there was that lingering feeling like physics should be the one.
Yeah.
And so one day I was discussing with my parents, and I told them everything, what my passion is and everything.
Yeah.
So they were supportive. They said, if that's what you want to do, that's what your heart is telling you to do, then why not go for physics?
Yeah.
So I applied to change my major
Yeah.
to science, to physics.
Yeah.
So, and the rest is history, I guess, where my will be physics.
You know, doing something you love.
Yeah. There's always that feeling like, if I had gone to engineering, would I have enjoyed it as much? Maybe I would have picked up on something, but I don't regret it because that's what I want to do. And that's what I'm doing. And if you're doing something that you love, you're not like working, right? You're just living your life.
Yeah.
Living your dreams.
Yeah.
So I get to say that.
So, I need to ask, when someone decides to, now I'm asking as someone who's ignorant in this field, now, so when someone decides to pursue the field of physics, right?
Yeah.
What's their career? What are the careers that someone can have after doing physics? Bachelor's in physics, master's in physics, PhD in physics. What are someone's careers?
Okay, now this depends on the area of physics you're working on. Okay, let's start with what I want to do, for example. If you're doing theoretical physics, there is not much application to it in like companies and stuff where you can go to the real world and apply it. But since you are doing research, basic research, so after you finish your PhD, you can go for postdoc, and you plug there as a researcher, and you just keep on continuing. Like you can go for professorship where you work in a certain university. You're doing your basic research, but you also get to teach certain courses for master's students or PhD students. So your profession would be those. Still, you're teaching courses, but you're doing your research also. You get to.
You're a researcher.
You're a researcher.
Yes.
So this is concerning theoretical physics.
Yeah.
Now there are other areas of physics, experimental physics, for example.
Okay.
Experimental physics, there's a lot of application. For example, if you're doing optic fibers and these things, you can go into that area of research. Nanotechnology, material science, and these things.
Yeah.
These have rich areas of expertise, let's say, or professions.
Yeah.
Because technology is advancing, and people are going to want to look into things that can enhance our technological advancement.
Yeah.
So concerning nanotechnology, fiber optics, and material science, this is a very rich area. So if people decide to go into this areas of physics, then there's a lot of job opportunities.
Yeah, but it depends on the country you're in.
Yes, it really depends.
Yeah.
For example, as an African country, I don't think we are there yet, because people at this time, at this point, are not looking for fiber optics or nanotechnology. There are far greater things we need to take care of before we get there.
We are still trying to fix our roads.
Yeah, exactly.
Yeah.
So if you plan to go to your back home or your country, and your country is not there yet, then
look for opportunities elsewhere.
Elsewhere,
yeah.
I would assume, because even the government would not invest much into these things because it's not going to benefit us at this point.
Yeah.
But maybe things might change. We're talking about, I don't know, 30, 20 years, a lot of things could change.
Yeah.
So that could be a new leaf.
What path did you choose, the theoretical or experimental?
Me, I chose theoretical. Even when I was doing my undergraduate, one of my professors, he was always pushing me to go to experimental. The same argument, the argument he was making was this same thing. Like if you go for theoretical physics, coming up with a new idea, a new breakthrough in theoretical physics is hard.
Yeah.
But if you go for experimental, you can. Still, it is that argument. Why didn't you go to doctor or being an engineer?
Yeah.
Still, you're doing physics to go for the money or those things, making a living.
Yeah.
Okay, still, it's very important for a lot of people.
Yeah.
But yeah, this thing I cannot stress it enough. If you're going for theoretical physics, there's not much reward into it.
Yeah.
But
so you don't like money, film, or you don't like money?
Maybe there are other ways to get money. Like I don't know. For example, for me, I like doing art. Maybe that could be.
You're an artist?
Yeah.
Oh, wow.
It's something I need to pursue. So.
You should. You should.
Yeah.
How is the art sector in your country?
Yeah, there are a lot of artists where they sell their arts in this art galleries.
Yeah.
So yeah, they make a very good living there.
Yeah.
But it's the same thing as for me physics. Art is also a passion, something the rest of the world might not follow it, or it's not something that I would say bringing money like constantly. It's not a constant job. Art is not a constant earning way of earning money.
Lucrative.
Yeah.
Yeah.
But it's a way of living. It's a choice. It's a life choice. So you're doing something that you love.
Yeah.
But if people are interested in your work, then it could be lucrative.
Yeah.
But yeah, the same thing as art and theoretical physics.
Yeah.
You have to have a lot of patience, I think.
Yeah.
You have to be patient. Work your way. It might take years or something, but once you get there, it's not something that would make you feel like you're wasting your time. You're not wasting your time because you're doing something you love, but at some point it would become something that would support your life also.
Yeah. So people doing theoretical physics, but I think by the time someone decides to do theoretical physics, it's just something they really love.
Yes.
They've forgotten about the money-making bit and everything like that.
Yeah, exactly.
Wow.
I cannot stress this one enough because to go for theoretical physics, you have to have a lot of patience. You have to let go of this. Just like we said, like making money.
Money-minded.
Mindset.
Yeah.
Because even at some point you will get to, if you don't have that mindset, you will get to a point where you will hate it, and it would feel like you have wasted a certain amount of time.
Yeah.
Maybe by that time it would be too late to even change professions, and it would be a life wasted.
Yeah.
So unless you know you want to do it,
yeah.
I would suggest making other life decisions.
Yeah.
Other decisions.
Whilst I was doing my research on your topic, the first thing I had to maybe, because everything was new to me, I didn't know what axions were, and so I had to find out what the axions were, what the gluons are, and then I had to find out what the Large Hadron Collider is all about. And I have to say it was really impressive for me to learn about it. So I need to ask, do you know how they make it possible for those two protons from different that are traveling different directions? at such speed, at such a speed, how do they make them meet? Such tiny, minute particles.
Yeah.
It feels so impossible. What are the odds?
I guess the odds are in your favor if they know what they're doing, I guess, right? First, to get them into those speeds. Basically, what they do is put them in this magnetic chambers where, actually, if you put a charged particle and you apply certain magnetic field into it, it starts accelerating. So you first you start accelerating it in smaller circles, smaller paths.
Yeah.
And we say protons. We say protons are being collided. So what they start with is hydrogen. Hydrogen basically is made up of one proton and one neutron.
Yeah.
One proton and one electron. I mean, so its nucleus is a proton and it has one electron rotating it. So if you remove that electron, what you are left with is just protons.
Yeah.
So basically, the protons for the Large Hadron Collider are basically hydrogen atoms without electrons.
Okay.
So they apply certain magnetic field to them so that they start accelerating. Then they are injected into even higher or bigger paths, a bigger circle, where even stronger magnetic fields are applied.
Yeah.
So they get to accelerate even more.
Yeah.
So what you are trying to do is every time the protons accelerate, you change the magnetic field, modify.
Yeah.
So every time they reach a certain place, they are accelerated even more,
Yeah.
So basically, when they reach the largest path, which is 27 kilometers in diameter, they are at a speed of nearly 99% the speed of light, which is very large.
Yeah.
Then what they do is actually they are accelerating the protons into two different directions.
Yeah.
One is clockwise and anti-clockwise. But when they get to reach the highest circle, they are actually passing each other at what we call four intersection points. So they are simply accelerating or moving in those circles, right? But there are 4 points where their paths meet. Okay. And it's not just one proton being collided, like it's just a bunch of protons. So actually this causes another experimental issue, because what you are doing is not colliding one proton at one proton. This is easier, you can find out. Easier, but still there's some difficulties into it.
Yeah.
But what they are doing is a bunch of protons are colliding with a bunch of other protons.
Yeah.
So we have the issue I've been telling you, like piled up. There could be interaction between even these protons. They haven't even collided yet, but these protons can be interacting. So this is another issue with it.
Yeah.
But yeah, there are ways to minimize this. We call them systematic uncertainties.
Yeah.
So, but basically, a bunch of protons, another bunch of protons, they get to collide.
Yeah.
And these four interaction points, as I have told you, like the surge state is the detector. These 4 places represent different experiments. We call them Atlas detector, just like we did, CMS, LHCb, and there are 4 different. They are looking for different physics scenarios. So yeah, basically this is what's happening. A bunch of protons circulating and interacting for interaction points. And a bunch of them.
Okay, I get that. Also, what is this about? What do I want to say? Okay, so I also heard of that same large hadron collider. I heard that it's dangerous. Is that true?
Yeah.
What makes it dangerous?
Okay, there is this running.
I've heard of explosions. Others, like, there are conspiracies about it. Why? Having a black hole, creating a black hole.
That's especially that one.
Yeah.
It's not just conspiracy theories. There are actually scientists who are warning those scientists not to go for higher energies even. The reason for this is, as I've told you, we know the standard model, how it works and stuff.
Yeah.
But what we are trying to do with the Large Hadron Collider is trying to find physics beyond the standard model, or new particles, new phenomena in these things. Some of this may include black holes, higher dimensions. So we know of 4 dimensions for our universe, right? 3 space and 1 time. But there's still theories which suggest that there might be other dimensions, more dimensions.
I want to ask you about that too. I want to ask you, but we'll get there later.
So basically, once we are running at higher energies, we are trying, if it actually works, our theories are correct. What we are theorizing is that there is a black hole. Black holes can be formed, or higher dimensions might exist in these things. So this is the concern with some of the scientists or the conspiracy theorists and stuff.
Yeah.
Is that if it does create a black hole, and a black hole in essence is always it attracts things. It eats things, and the more it attracts, the larger it gets.
Yeah.
So if it gets to it, I'm not sure. Okay, I'm being maybe a conspiracy theorist here now because I don't exactly understand the physics behind it. But what they are suggesting is that the Large Hadron Collider could be the end of us, because it could destroy
consume the Earth.
Consume the Earth.
That's something.
But it might not get there. Actually, might.
Now I'm gonna be seated there. Oh my goodness! I hope these people are doing well at the Hadron Collider.
But it's conspiracy theory because they know what they're doing.
But it could be true.
It could be true.
Maybe it's true, but they're making us feel like it's a conspiracy, since some of us don't know the physics. We don't know the.
Unless someone evil is trying to destroy the universe. Because what I mean by this is, black holes are actually being created, but they are at a quantum level that they are always like existing and then annihilated, exist and then being destroyed.
Being created at the collider.
At a quantum scale, quantum scale.
Okay.
But they're so unstable that they don't exist for a very long time. They also annihilate and they die out.
For someone who doesn't know what a black hole is, could you explain to them?
Now black holes. I've talked about the standard model. I said general. This gravity is another topic of its own. Because there is another theory all over for it, and we call it general theory of relativity. So once Einstein came up with his equations, some people started solving those equations. We call them the Einstein field equations. When you solve for some of them, they try to find out that there is a certain phenomenon in the universe that might exist, which is called a black hole. The name black hole was later termed, but basically what it says is that the way general theory of relativity explains gravity, Newton said if anything has mass, it attracts. So the Earth is massive, it attracts the moon, it attracts an apple falling, these things. But once Einstein came, his theories tell us that it's not the pull of the Earth, it's actually the Earth bends what is called space-time.
Okay.
Anything that is moving in a flat space-time is moving in a straight line. But once you put an object there as massive, for example a bowling ball, if you put a bowling ball in a base shape, the base shape curves, and this curvature is what corresponds to the curvature of space-time. Okay. Now if you try to put the same object and try to move it in a straight line, you cannot move in a straight line. It has to bend with the curve of the space, the bedsheet or the space-time in this case. And this is how Einstein tried to explain how gravity works. Now we can think of the bowling ball as the Earth, and we can think of the tennis ball as the moon or the satellites, anything that's moving around the Earth. So massive objects, they bend the space-time. But once the equations are worked out, Einstein's field equations, there are certain objects in the universe where their masses are so massive that the curvatures on the space-time, they cause these curvatures that not even light passing through this curvature can escape. And this is what's called black holes. Their masses are so high that they curve the space-time really. They have really high curvatures.
What's that original mass that was so heavy to an extent of making that large curvature?
Yes, the origin of a black hole is from stars. Stars, actually, our sun is massive, but it's not as massive as compared to certain stars we have. Even when our sun dies out, it will not create a black hole. It has to have a certain mass to create a black hole. So these supermassive black hole stars, they are always in a constant balance between two forces. Gravity is trying to put everything together, like pull everything towards their centers. And since they are stars, they have this nuclear reactions, hydrogen, and this is basically how they get their energy, how they shine light. And this heat and these explosions, they're trying to burst out the star. So we have this balance between these forces, but eventually what dies out is the nuclear reactions, because hydrogen fuses with helium. It gives us a very large amount of energy. Helium fuses with other materials to make even higher elements. But as this goes, they reach a point around iron or something where they are so massive they don't have any nuclear reactions. So basically what is happening is the star is killing itself. It's using its energy to make more stable elements. So the force that's meant to keep it exploding or having its size or shape, it's dying out, but gravity is always there. Gravity is because of the mass. So what will happen is, it will get to a point where everything is crunched together, it bursts out, and what is left is that dense leftover matter. This dense leftover matter creates a black hole.
Yeah.
So dense, so massive, that this dent, it causes this spaceship, is so massive that everything would be pulled into it.
Yeah.
And this is what we call black holes.
Yeah.
There are certain theories that suggest they may be created at the quantum scale also. So this is what we were discussing before for the Large Hadron Collider.
Yeah.
But mostly they are. The reason even they are trying to, for the black holes, they exist at the quantum level, is another. The ultimate goal of physics, of theoretical physics, is a theory of everything. We can explain the small world, the quantum world, with the standard model. We can explain the massive world with general theory of relativity. But there is no one theory that combines everything together. If you try to put them together, we have theories, for example, string theory and quantum gravity, we call them. But they suggest black holes at the quantum level in these things. Okay? So what we are trying to do at the Large Hadron Collider are trying to confirm these things.
Yeah. Yeah. What do you want to ask? I don't remember. How many black holes are there?
So far, they have gotten images of 2.
I remember you saying that we can't see a black hole.
Yeah. As I have said, there is a certain point on the black hole which is called the event horizon. If even light reaches this point, there's no point. It's not a point of return. Everything is sucked in. So that's how a black hole actually got its name. Nothing can escape. It's not even light, so you cannot see it even. And the only way
How
to
did you get a picture? But how did they get a picture of the black hole if we cannot see it?
Yes. Now, what do you get a picture of? For a black hole, as we have said, it cannot be seen.
Yeah.
But its gravitational effect is still it affects the objects near it.
Yeah.
So the stars that are near it, they will be affected that they are moving around this black hole because of the gravitational pull. But what you would see as an outsider is that something is rotating, the star is rotating, you can see the star, but it's rotating around nothing. The nothing is because we cannot see it, but it's still there.
That's crazy.
So you just see a star that's rotating around nothing. So this is how you confirm the existence of black holes.
Is it rotating at a high speed?
Yeah, actually, yeah.
Wow.
This their speeds can be even very large. Actually, speeds to massive objects would not seem very high. If I'm not mistaken, actually, the Earth is moving around the Sun at a speed of I think roughly I would say 1,000 kilometers per second or something. That's 1,000 kilometers per second. The Earth is moving around the Sun. 1,000 kilometers, that's at 1 second it has moved 1,000 kilometers.
What?
But as living on Earth, we don't even perceive this speed. And
the people at the International Space Station, do they see the Earth moving like this?
Also, that's also an interesting question because for them it would appear stationary even. The reason for this is they are also moving at that speed.
At that
because
speed, yeah.
They are always at a point where they are always at a point above a certain point on Earth.
Yes.
To keep that, the Earth is rotating. They are also rotating with it.
I remember having a conversation with someone where we were asking ourselves, we were talking about how do these people calculate coming back home?
Yeah.
If the Earth is moving like this, how do you calculate to come back? Like at this time, the Earth will be at this point, so then now also Earth will be. I wonder how they make those calculations.
I would recommend a movie, by the way, here, Hidden Figures. There's actually a point they discuss this because it's really difficult.
Yeah.
Because you have to account for a lot of parameters, and since you are dealing with people coming over, you have to be really precise to get there. But rocket science is actually rocket science. It's hard, and for that exact reason, it has to be precise.
Wow. Wow. So I want to talk about, I call them conspiracies because I'm not a physicist, and sometimes listening to these things they really sound like conspiracies, even if it's science. It's crazy. So you've probably heard of the Schrodinger's cat thing, and is the cat there or not? And then somehow now they're telling us that all because of that theory now it shows existence of parallel universes and stuff like that. Please explain what's going on.
I know these questions. Yeah.
Is there a person like me
Maybe
somewhere?
I'm interviewing you right now in another universe.
No, that's crazy. And I'm the physicist and you're the interviewer. Okay.
Probably.
Tell me about that.
Right about when quantum theory was being theorized, as I've said, Max Planck is the father of quantum physics generally. But a lot of other scientists also came up that started working on the mechanics of it and everything. So the person actually is Schrödinger. Schrödinger was the first person to give us an equation that explains this quantum world. It's also given the Schrödinger's equation. But when they were trying to interpret, there is a certain parameter there, represented by the Greek letter psi. If you apply it to certain phenomenon, it gives the right results, which agree with the experiment. But the problem is, what does psi refer to? What is it? What is it? Is it representing position? Is it representing momentum? Or what is it representing? There is still a debate on how to interpret this wave. We call it the wave equation. Okay? The wave equation. But what actually is waving? What is it? Is it amplitude? As I said, there's a lot of debate. Even Schrödinger himself, he was actually the one who came up with the Schrödinger's cat experiment. Yeah. It's a thought experiment, but he meant it to explain the absurdity of the notion. Yeah. To give a brief a brief thing into this, Max Born suggested one interpretation. He suggested that when we are talking about psi, the wave equation, we are talking about probabilistic nature of the particle. Every particle has associated with it a probability wave. And then when we use this probability wave into the Schrödinger equation, we get what we need. So by saying this, we are saying the quantum world is probabilistic. So to explain where an object is, you have to work out the math, and you would end up giving a probabilistic result of the position. You can say within this limit or within this range, there is a 50% chance of a particle being here, or 70% chance of here, or it has 80% chance of having this speed on these things. So everything was probabilistic, and the way the wave equation, we call it okay, forgot. Basically, what I'm trying to say is that's like the quantum state. The way it would work is, if you're not making any observations on the quantum state of particles, they can have whatever value they can have. What I mean to say by this is, a particle could be here, a particle could be there, in the middle, anywhere. But once you make the measurement, then the particle is where you find it to be. It acquires a certain quantum state. But before the measurement, it can be anywhere. So basically what we say is the quantum state collapses at this point. It becomes a certain value. Okay? Now Schrödinger suggested this. Let's say in a box, there is a quantum state, a certain particle or something, and a certain quantum state. So you don't know when it's going to achieve that particular state. So, but we have this arrangement. If it collapses, if it has, for example, a spin up state, then it will trigger another mechanism. That mechanism is, it will cause a certain valve to hit a poison. This poison would either be triggered or not triggered based on the quantum state of the initial particle. And there is also a cat inside the box. If it gets the poison, it dies. If it doesn't, it's alive. But everything is sealed. Okay? Now you're outside of the box. Now what does it imply when we say when you make a measurement, the particle acquires a certain state? Right? or the quantum state collapses into a certain value. What this implies is, if you're not looking into it, is the cat dead or alive? For it dead to be dead or alive, the poison has to be released. For the poison to be released, the quantum state has to be in a certain state. But we said that if you're not looking into it, it can have any value it wants, any value it's possible for it to have. So, without looking into the box, what they are saying is, the cat is both dead and alive. It's once you open the box that once you open the box, you see into the quantum state of the particle. It will have a certain value. So, for example, if it's up, the poison will be released, the cat is dead.
Yeah.
If it's down, it's not released, the cat is alive. But this can only be done once it's open. And this actually puts everything into a quantum state, because you opening the box and seeing depends also on the quantum state of that particle. Because if you open the box, you either see the cat dead or you don't see. There are two versions of you, which see the cat dead, which don't see the cat dead. Based on this, maybe your wife could be repelled by the smell of the cat, and she would divorce you or something. And there's another universe where she doesn't. So opening the box creates this many worlds where a certain decision can have a different impact. We call it the many worlds interpretation, or the parallel universes. This suggests that at any given time, if there is a forking between two events, where the results can be just like the cat, where they can have two states. The universe is being fractioned into divided into. So every decision has a. So we are always.
Those are infinite then. Yeah. Infinite possibility. I may not have decided to come and sit here with you.
Yeah, and there is a play. You might have come and then go back or something.
There's so many.
Infinite, literally infinite, the universes.
Okay.
But all this stems on the fact that the quantum state of a particle, if you don't look into it, it can be in all of its quantum states, all of its possible quantum states. It's only when you look into it that it has a certain. But this is one of the interpretations. This is called the many world interpretation. There are also other, the Copenhagen interpretation. But until now, there's no concrete evidence that the one is better than the other. But what we can be sure of is the quantum physics, almost all the experiments, everything we have been saying about the Large Hadron Collider, standard model and everything, it's a quantum theory. So we know it works, but we don't know what the interpretation is, what psi represents. This is the Schrodinger's cat.
So let me ask you, as someone who understands physics, right?
Mm-hmm.
Do you have issues, or do you have points where when you laugh, when you're watching movies and they're just throwing physics theories around? Oh, should be Schrodinger's cat experiment. Yeah. So they randomly throw. Do you have points where you laugh and you're like, what?
Sometimes it makes you mad. Actually the best one, Big Bang Theory, the series.
Were they lying
they're always accurate.
Oh,
I think they already have actually a physicist who takes care of these things.
Yeah.
So the Big Bang Theory, everything they say is accurate.
They weren't lying. String theory, whatnot.
Everything is real.
Yeah.
What bugs me is this Avengers movies, because there's something they cannot explain. They just say quantum, nanotechnology. Just put in words there.
And as they understand, they're like, yeah, sci-fi. Wow, yes, technology. Yeah, physics.
They should try a little harder.
Yeah. But at least a movie that is going to be watched by millions and millions of people. The least they can do is just get one physicist.
Yeah, just one physicist. And it doesn't have to be every time. They just say quantum at a certain point. just for that one, make it a little bit.
Do you have any example of something that has been said in a movie and you were like, what? That's a lie.
This, for example, in Avengers, that in the game, they just show that because actually they get into the quantum world. They are always putting. They don't even say, for example, the literal term or the actual technical term, quantum entanglement or something. They just say quantum physics or it's quantum. Okay, quantum actually means small. That's the literal meaning of quantum.
Yeah.
But yeah, actually I would understand in a sense that whatever they are trying to portray has not been discovered yet. There's no verification for it because sometimes they go into the quantum world and they live there or they fight there at that level. We don't know what is that's like. So
they're really fighting at the
yeah, there's a person at the quantum level, right?
What?
But yeah, I would understand. Even I am saying quantum level at the quantum world. So yeah, I would understand at some points that you can use generic terms, but at other times where it needs elaboration, just for us nerds, put something there.
Yeah.
Or yeah, we can watch Big Bang Theory.
Yeah. So do you have any advice for upcoming physicists?
Yeah, I have mentioned it in the beginning. Going into physics, pursuing a career in physics requires a lot of patience, a lot of dedication, a lot of hard work. Because personally, for example, there were like 2 semesters in our master's study where we had to work 12 hours a day, 7 days a week. Basically, go to the lab, those simulation, math, graph, theta, everything I've told you about. Because you do something, it doesn't work out. You have to try another way. So for 2 semesters, I will go to the lab at 8. You just go out for lunch and dinner, and then the same thing. You go out of the lab at 10 in the evening, and this goes on 7 days a week. Even Sundays are there. So basically, you might even be a little bit away from your society, from friends and stuff.
Social life is going.
Yeah. Because in order to succeed, you have to sacrifice that time.
Yeah.
I'm not saying that it should always be that way. If you actually manage your time, you can have everything you want, but you should also prepare for this kind of life. It's going to require a lot of hard work. Hard work is going to require a lot of dedication into it, a lot of patience, and most of all, you should go into it if you love it. If that's something, if that's your passion.
I mean, you're only spending 12 hours a day in something if you love it.
Yeah, exactly.
What did I want to say? Did you finally find what you were? I mean, you graduated, so I'm under the perception that maybe you found out what you were looking for.
Actually, from my masters, I have been doing this LHC work and these things. I'm still going to continue for my PhD.
Yeah.
And hopefully, until now, I'm trying to figure out what signals to go for, what to look for at the LHC. But yeah, I feel like this is another step I'm going to have to take, and I want to take, and hopefully it will be successful. We'll see in the future.
Good luck.
Thank you so much.
And hopefully in 2027 I'll remember Film did the particles mix together the way you wanted them to?
Yeah.
Did you find what you were looking for?
Hopefully.
Yeah. Alright, that has been our conversation today, and I hope that someone picked something from it, has been inspired by it. I have learned a lot from you. Now I have something to talk to people about. I'm gonna going to be looking really intelligent, talking about black holes and the Hadron Collider and I've loved this conversation, honestly. Thank you for allowing me.
I enjoyed the conversations as well.
Thank you.
Thank you.
Alright. Bye, guys.
Bye.